So, today in this session we are going to see one of the common application of the crystal diode as a rectifier. So, crystal diode, that is the PN junction, is used in rectification purpose, that is converting AC into DC. So, nowadays this cell phone charger what is just basically a rectifier. So, we have already seen in the previous class that a crystal diode, a PN junction, this is the junction, this is P and N. So, this PN junctions conducts very heavily in this direction and forward biasing, and during reverse biasing it does not conduct electricity. The current is in microamperes in reverse direction, and in forward direction the current is in milliamperes. So, some circuits, some common circuits may not be able to detect or that microampere or nanoampere current. So, we think that there is no current in the reverse current. So, we use a symbol like this to denote this PN junction, this symbol. Now, this symbol means this side is P type and this side this is N. So, this symbol has an arrow and this a line. So, the arrow tells that if you give current in this direction, it will allow the current to propagate, and this line tells that if you try to give this current in this direction, then that current will be stopped. Then this PN junction will not allow the current to flow in this direction, because in this direction it will be forward biased, and in this direction if I will try to give this direction, then the junction becomes reversed biased. Now, this PN junction offers a very less resistance to the forward current of the order of, you can take 1 to suppose 10 to the power 3 ohm. That means 1 to 1000 ohm, up to 1000 ohm, means generally it is 50 ohms, 100 ohm, depending on what type of this diode is. So, maximum 1 to 1000 ohms, so nearly 1000 ohms. Whereas, in reverse bias the resistance is in the order of 1 lakh volts, 1 lakh ohms. That means this 1 lakh and more than 1 lakh, suppose 50,000 on 1 lakh times that this value. So, that is in mega ohms. So, that is why you see the PN junctions offers very less resistance to the forward current and very high resistance to this reverse current. Thus, we see that the unidirectional ability of a PN junction to conduct current heavily can be used in rectification purpose, that is converting AC into DC voltage. So, let us first see half wave rectification. So, now let us see half wave rectification. So, in half wave rectification we use our circuit like this. We have a transformer coil and we have given an input in the transformer coil, and in this input we give a AC input. Now, this is the transformer and we have connected this AC input to the primary of the transformer, and now we have this secondary coil and we have connected a PN junction to it. In the secondary coil, a PN junction in series with a load resistor is connected. This is the primary and this is the secondary. The advantage of this transformer, this is generally step down transformer depending on how much voltage we require. The two important points it serves. Number one, in this user circuit, you see we are going to take the output across here. This is output. So, it insulates the output circuit with the high voltage AC input. So, suppose I am giving 220 volts and we are going to use my cell phone to charge for charging, and output I require is 10 volts. So, my output circuit will be insulated from the input circuit. So, there will be no shock and no damage to my instrument. And so, you see, and second is, suppose this is 220 volt input, I can just by changing the ratio of the turns, the number of turns in the primary and secondary, I can take the desired output voltage here. So, voltage down can also be done. So, suppose here 220 volt and I want something 10 volts. So, there should be nearly 22 rounds, 1:22 turns in this transformer coils. So, now let us see how this rectification can be done. So, let us assume this point as A and this point as B. Let us call this point C and this point D. And let us denote the input. So, what happens? Let us see that here the sinusoidal input here, because of this mutual inductance in the transformer, the alternating current will be induced here, and so here V input will be there. That will be a alternating input. So, now let us see the input voltage which comes at A and B. Let us denote it. This is the input voltage. So, now here let us see, this is input voltage, that is we get at AB. What input, you see what I am giving here and what we are getting in the secondary, let us plot V in. So, this is one cycle and next another, then this, then 4. So, this is one cycle, another cycle. Now, we will see, let us compare it. So, we will plot V out. V out is across the load resistor, that is the potential difference between C and D. Now, what happens? These cycles are positive cycles and these cycles are negative cycles. This whole concentrate here, positive cycles and these negative cycles. So, let us assume that during positive cycle A is at higher potential than that at B. So, let during positive half cycles A is at higher potential than at B. So, suppose A is at higher potential, you say just imagine B is at 0 and this, suppose I say it is at 0 and it is at suppose 10 volts. So, you see what happens, this is at higher potential, this is your P type and this is N type. So, the diode becomes forward biased. So, let during the positive half cycles A is at higher potential than B. The diode then becomes forward biased and conducts. The current flows from D to C in the load resistor. So, the direction of current is from D to C in the load resistor. So, you see this becomes the voltage in the output voltage we will get is this. So, this will happen every time this is forward biased. Every time it is forward biased. Please see this diagram. Now, let us see what happens during negative half cycles. So, let during negative half cycles, the point B is at higher potential than A. So, suppose I say this is V is 10 volts and this is 0 volts. So, what happens? The PN junction in this case becomes reverse biased and is not conducting. So, no current flows in the circuit. So, here whenever this is negative cycles, minus cycles, the current flowing is 0. So, current is conducted only in positive half cycles. That is why its name is half wave rectification. What is important point, what is our concern here is that during negative half cycles the diode becomes reversed biased, and we must take care that the reverse voltage, the maximum voltage, this is minus V max and this is plus V max. So, this should not reach the peak inverse voltage, that is the breakdown voltage of this diode. So, once this voltage, if this voltage is more than the peak inverse voltage, breakdown voltage, then the junction will break down. So, this is our concern only. So, while we do the rectification, we should keep in mind that the maximum reverse voltage should not be more than the peak inverse voltage. Now, let us see the rectification efficiency of this half wave rectification. Now, let us calculate the efficiency of our half wave rectification. So, rectifier efficiency is given by we will denote this efficiency by eta is equal to DC output power upon AC input power. This is the expression for the rectifier efficiency for any type of rectification. So, we will see for half wave rectification. So, first of all we have to find out this one and then this one, and then we will take the ratio. So, first is DC output power. Let us calculate what is DC output power for this. So, before calculation we must know that this is my time, and suppose the current, the output power means the output circuit, the current is suppose given as this is DC. So, like this it will be there. So, this is rectified half wave rectified DC output current. Now, you see this current is passed through some filter circuit, and so we make this something like this T and something this is rectified output. So, once we place it through some filter circuit consisting of some capacitor, what will happen? It won't allow it to decay abruptly to 0. So it will smooth like this, and so we will get a IDC. That means this will be the rectified DC after some filtration. That means I want this, what is this IDC for this current? So I have a rectified, half wave rectified output, and if I filter it through some capacitor circuit, then we will get this IDC. That means average value. So IDC will be equal to, integral this function I into theta by, suppose I take from here to here, this is pi and this is 2 pi. If I plot theta here, suppose, so it will be 1 by 2 pi, and I will be writing I as I naught sin theta. Suppose here to here function is sin theta and d theta, this integrate from 0 to pi by 2 pi. So this is how to evaluate the average value of this current, that we have already done in our alternating chapter AC. So it is integration of sin theta is minus cos theta from 0 to pi, that is I naught. I naught is the maximum current, this is the maximum current. Now my cos pi is minus 1, so 1, then plus, then cos 0 is again 1, so that is I naught by pi. So the value of the DC current I got is I naught by pi. So thus DC power output, we have DC power output is equal to I square R. So it will be I naught square by pi square RL. The load resistance were RL and output is always taken along the load resistor. So this is my DC power output. Please take down this. Now let us calculate what is the DC AC power input. AC power input. Now what is the AC current? You see, AC current let us write is at, for this half wave rectification, let us AC power output we will write as I require IRMS into R. So the IRMS for a half wave rectified wave is actually I naught is the maximum by 2, I naught by 2. If you have done AC, you will be knowing, otherwise I have to derive this result. So you see, where you should remember IRMS means root of mean of square of, that is I square dt over the whole time period, or if you write in terms of theta, then will be like this. So or it can be further written as root of this mean of I. So I naught square sin square theta, if I write in terms of theta, then theta varies, if it is only half wave 0 to pi and this 0 to 2 pi, we have to do like that. Let us do it and see it comes out to be I naught by 2 or not. Now you see here IRMS is equal to, this is, let us calculate this root over, this is I naught square by 2 pi, then we have sin square theta, integration of sin square theta d theta. So what we do, we take 2 here, so we will again take 2 here, so it will become 4. Then 2 sin square theta, this will become I naught square by 4 pi, let us root of 2 sin square theta from 0 to pi. Now we can write this as 2 sin square theta as 1 plus cos 2 theta d theta integration from 0 to pi, that to the power half. Let us write. Then again it is I naught square by 4 pi. You see here, this is theta plus this is sin 2 theta by 2, limits from 0 to pi to the power half. This is the IRMS for half wave rectified input. So you put this pi plus sin 2 pi is 0 minus, then it is 0, so to the power half. So you see we got pi cancels, this to the power total half, so we got pi cancels, so this is only I naught by 2. So which we have written is as the expression. So if you know directly you can write, otherwise we have to calculate in this way. So the RMS value for a half wave rectified wave is given by I naught by 2. So we have AC power input as IRMS whole square into, you see input is given across the whole output circuit. So the IRMS is given across the whole circuit, that is diode plus the external resistor RL. So the total resistance is RF plus RL. So this is IRMS, that comes out to be, this is I naught square by 4 RF plus RL. This is, keep this point as equation 2, very important point. Please take down this. So now let us calculate the rectifier efficiency. Half wave rectifier efficiency eta is equal to DC output power upon AC input power. So we have DC output power as I naught by pi was the DC current, so I square, and the load resistance was taken across. You see, just recall this circuit. This was the diode and this is my load resistor RL and this is my secondary coil where we have given an input V in. So this has a forward resistance RF and RL here. So the output is taken across this point only. So only RL is involved. Upon DC power, AC power input now. AC power is IRMS, that already we have calculated this AC power input as I naught square by 4 RF plus RL. So this efficiency comes, I naught cancels out. So this is 4 means it will go up, 4 by pi square RL by RF plus RL. This is my efficiency of a half wave rectified wave. So eta will be 4 by pi square 1 by 1 plus RF by RL. We can write this in this format also. Now maximum efficiency, maximum will be when this will be maximum when this is minimum, this minimum when this is 0, so RF is 0. So is equal to 4 by pi square when the forward resistance, when this term is 0. So when RF by RL tends to 0, means either load resistance is very high or this. So when this factor becomes 0, that is RF is very small. So if forward resistance is very small, then this efficiency will be 4 by pi square. So you see N max in terms of percentage, you see this pi square is nearly 10, its value is nearly 10. So, 40%, it is generally, this is 40.6%. So, pi square has a value nearly equal to 10. So, the maximum rectifier efficiency for half wave rectification, we got it to be 40.6%. So, please take down this. So, now let us take an example to know the efficiency of this half wave rectification. So, the applied input AC power to a half wave rectifier is 100 watts. The DC output power obtained is 40 watts. So, input we have given is 100 watts, output we are getting 40 watts. What is the rectifier efficiency and what happens to the remaining 60 watts? Again see, the applied input AC power to a half wave rectifier is 100 watts. We have given 100 watts input and we are getting only 40 watts output. So, what is the rectifier efficiency? So, the rectifier efficiency eta is equal to the DC output power is 40 and 100 power watt was the input. So, this is 0.4, that is 40%. So, the 40% is the rectifier efficiency. Now, it seems that we have used only 40% and remaining 60% is wasted. This is wrong. You see, we are using only 50% of the part, only half cycles we are using. So, remaining 60% we can't say it is wasted. So, in order to see how much is wasted, we have to calculate how much we are using it. So, power efficiency eta power will be equal to, you see we are using out of 100 watts only 50 watts of AC input. Other half is not used up at all because the diode is not conducting. So, we are not out of 100 watts available, we are using just 50 watts. For 50 watts power, our diode is dormant, it is non-conducting. So, how much actually power we are utilizing? So, power efficiency of this circuit, we are using 40 watts. When we are withdrawing 50 watts, we are using 40 watt. So, that is 4 by 5 is equal to 0.8, that is equal to 80%. That is, we are using 80% as power efficiency. So, important point, it seems that we are getting only 40% or 40.8% something as half wave rectification, but we should be cautious that we are not using the all input power, we are using only 50% of it. So, how much actually we can say it is wasted? So, simply 20% we are not able to use up, only we is using 80% of energy which we are consuming in rectification.